All right, can everyone hear me all right? Sorry for the delay, there was technical issues. So I work on Altera's high-level design compiler team, specifically on our OpenCL compiler. And today I want to talk about how we use LLVM to generate custom data paths to target an FPGA device. So I almost have to start by saying FPGAs are really awesome. They're used in a really wide range of applications, from automotive infotainment systems to medical imaging and network storage. They offer fully configurable architectures. They're low power, customizable I/O, and they'll keep up with Moore's law. So the problem with FPGAs is that design entry is extremely difficult. And typically you have to input your designs in a hardware description language like Verilog or VHDL. And this is a lot like programming in assembler. It's done at a very low level, the register transfer level, which means that you have to describe every single piece of hardware and its execution in every single clock cycle. So it's extremely detailed. And the amount of code you have to write in order to describe what would be the equivalent of a relatively small software program is quite large, and it can take months to implement. It's also very, very difficult to test, because as you can imagine, if you miss one register transfer, you could have a bug that takes you a very long time to find. Sort of a separate problem from that is that there are a lot fewer hardware designers out there than there are software designers. And so it's more of a rarefied skill, and it's harder to find someone who will be able to code up your algorithm or your function in Verilog than it is to find someone who could work in C. So one of our goals at Altera is to raise the level of abstraction to reduce the barrier to design entry for FPGAs. It's a lot easier to describe something in C than it is in Verilog, just like it's a lot easier to write in C than it is to write in assembler. You can increase your productivity when you raise the abstraction, and it becomes simpler to test and verify because there's already a plethora of tools available to help you do at least the functional verification. And again, because there are so many more people who can write in C, you have a larger potential pool of candidates who can do design now. And you can open up FPGAs to a much larger audience this way. So it sounds promising, but how do you map a higher level language onto an FPGA? So our vision is to leverage the software community's resources. And I have to say that LLVM is a great compiler framework. It has a lot of things that are really great about it. We love the IR, and being able to use it in the future to extend it to different languages probably its best feature. So we've modified LLVM and added an entirely custom backend to generate Verilog HDL, as opposed to generating assembler. And that's the single biggest change, but there are lots of other changes we've made in the compiler. So our higher level language of choice is OpenCL, and it's an industry standard heterogeneous compute language that targets a sort of a host and accelerator model. And it offers functional portability across platforms. It doesn't guarantee performance portability, but if you're writing something for a CPU, you can take that same code and run it on a GPU. Or if you're writing on a GPU, you could take that same code and run it on an FPGA, and at least it will be correct. As usual, if you want really high performance, you need to know about your architecture, and you're probably going to have to tweak your code. But being able to get up and running quickly is a huge bonus, especially in the FPGA community, where typically design cycles are very long. So in order to be conformant for OpenCL, you have to pass over 8,000 tests. And this might not sound that big, but we're the only FPGA vendor who's been able to do so. And the amount of compile time it took for us to do this was several CPU years to calculate all the binaries, or compile all the binaries up. So it was not a trivial task by any means. The really big idea behind OpenCL is that you're defining an n-dimensional computation domain, and you're going to execute threads on the same sort of code, but with independent pieces of data. This is a lot like SIMD. So instead of your traditional loop, where each iteration is going to do a different sort of same calculation with different data, in OpenCL, you're going to define a kernel, and the loop becomes implicit, where each thread is now operating on a different piece of data. So What are the differences you have to think about when you're targeting an FPGA versus a CPU? It's important to know that FPGAs are really, really different. They offer massive fine-grained parallelism, which leads to very, very high levels of instruction-level parallelism. They're completely configurable, which means that any signal on the FPGA can route to any other block. And they offer huge internal bandwidth. With the amount of on-chip random access memory and registers we have, we can perform very, very large amounts of data movement very efficiently and cheaply on the FPGA. That being said, it's a lot different from a typical CPU. We don't have a call stack. And one of the implications there is that we inline every function call, and our kernels are flat. We also don't provide dynamic memory allocation. And this doesn't really tend to hurt us because in high-performance computing, you're generally going to want to pre-allocate your memory anyways. The instruction costs are also very different. We have some instructions that take a fraction of a cycle to implement, and we can chain many of them together in a single cycle. We also have a lot of instructions that can take over 100 cycles to complete. And in terms of resources, we have instructions that are literally free, whereas we have some instructions that take a very large amount of resources on the CPU, or FPGA. Some of the stuff that's really cheap, as you might guess, is bit manipulation, ands and ors, masks, simple shifts, simple arithmetic. It's all very cheap and easy to implement on an FPGA. Accessing external memory, on the other hand, tends to be expensive. And until recently, floating point was quite expensive, but we're releasing a new FPGA that has hardened dot product cores on the FPGA, which will dramatically change the kind of algorithms you're going to be able to run on the FPGA and what it takes to implement them. So we also don't have any fixed number of program registers. And one of the things we do with that is that we aggressively promote anything and everything we can into registers. We'll do non-constant shifts, which I know the CPU world likes to avoid, in order to get things into registers. We've made a lot of changes to LLVM to get all of mem2reg to work in every case we can find. We also don't have any fixed memory system beyond going to external memory. On chip, we completely customize it to your program. And we have small chunks of random access memory that we can configure into almost any architecture you need. And the nice thing about that is from a user's point of view, you can just view it as having as many load store ports as you need to your memory. So normally when you're targeting an architecture, you're mapping your program onto a fixed set of hardware. But in the FPGA, there's no fixed architecture. In a sense, there is no architecture at all. And this is both a benefit and a curse. Because there's no fixed architecture, we'll create something that is hyper-specialized to the program you've given us. And we're going to knock away absolutely everything else we can. We're going to streamline it down to its essentials. And it's not going to hurt us because the FPGA is completely reprogrammable. When you want to perform a new task, all you have to do is reprogram the FPGA with another hyper-specialized program. Because you can always make really efficient use of exactly what you're performing. And the FPGA can perform just about any function you need. So our program is going to define our architecture. And that's what we're going to create a data path out of. And instead of being constrained by the available hardware, we're constrained by the resources on the chip itself that we have to use to create the hardware. So it's quite a bit different model than your typical CPU compilation. So how do we go about generating a data path? At a very high level, you can liken an FPGA data path to an unrolled CPU. Here's a very, very simple CPU. It can only do a few instructions. It can load an immediate value, or it could load something from memory. It can store back into memory, and it can do some arithmetic like adding and multiplying. And again, here's an extremely simple program that will exercise all of those instructions. Now, in the CPU, we're going to perform temporal unrolling, and we're going to reuse the same hardware and over again. But not all of it will be active each cycle. And I have that laid out here for you. the hardware that's active in each cycle for these instructions. In an FPGA, we'll actually perform spatial unrolling. And as soon as you start spatial unrolling, you can really start to specialize your hardware. Because we know what instruction is going to be executed in every cycle, we can just get rid of the fetch and the decode units altogether. It's unnecessary hardware. We can also see that there's a lot of grayed out logic in this picture, and that's all hardware that's not active in a cycle. We don't need it. So we're going to remove the unused ALU stuff, and we're going to remove the unused load store units. And now what we have next is a really big shift. We're going to drop the register file altogether. And instead, we're going to wire up registers directly to each other. And you can see that now state is just flowing through our data path instead of being stored in a more central location. We still have a little bit of dead registers. We have a few dead registers here, and we can get rid of them. And here we can see now the fundamental data path is taking shape. Instead of a register file, we're carrying live data directly through the pipeline, like a pipeline CPU instruction. And your live ranges define how much data you need to be carrying in each stage. And this has a direct impact on how many resources you need to implement your algorithm, how many resources your algorithm will take on the chip. Now, this isn't fully optimized, and one of the things our backend will do is it'll solve a scheduling problem in order to minimize the amount of live state carried in your program. And so we can just reschedule this and really reduce the number of registers we have. And now what we see is we've created a piece of custom hardware for this simple program, but the FPGA data path is just that. It's a completely customized program, and it's your algorithm implemented directly in hardware. So we'll take a step back now and look at a data parallel kernel. This is a very simple vector add. And a lot of normal processors would want to do this in a SIMD fashion. And that's in a way the way OpenCL was designed. Each thread is operating, again, on a different piece of data. But that's not how we implement our data paths. As we saw before, it's about carrying data through registers. So what our data path looks like for this is some functional units separated by registers, and we're going to feed a new thread into this pipeline each cycle. And so as the data travels through, we now have space available to feed in new threads. And so when we're storing out thread 0, we can be adding thread 1, and we can be loading thread 2. And in the steady state, we're using all of this hardware efficiently. So at a high level, what does our compiler look like? And how do we go about creating a file that you can run in hardware? So at a very, very high level, we're going to take your source code. And it may sound silly, but we do single source compilation. We run it through our compiler and produce a binary file that you can program your FPGA with. Internal to our compiler, we run through the regular stages, front end, optimizations, and back end. The difference is our back end produces Verilog HDL, and we feed that into our Altera Quartus 2 software, which runs through the normal CAD steps of placing and routing, fitting your design together, and worrying about the timing analysis, and figuring out a clock speed that you can run your circuit at. So our front end parses OpenCL, which is essentially C99. It has a few extensions and a few restrictions, but at its core, it's C99. Our middle end optimization stage is essentially 2 phases. At first, we run Clang 03, which had quite a few changes done to it. But then we run a lot of passes that target the FPGA specifically. And we actually made it so that we try and do as many transformations as possible on the IR. We've gone away probably from what a lot of the community does, and we do very target-specific things in IR. Our backend will create and schedule an elastic pipeline data path, and it's going to write out the Verilog file. We try and keep the backend as simple as possible compared to our optimization stages. And probably the most interesting thing is we're using the IR to describe an architecture. It's not just a set of instructions going to be run on some hardware. We're going to describe the whole program's architecture with our IR. So Unfortunately, it's not as simple as just unrolling hardware and wiring things up. If you do this naively, you're quickly not going to fit any more logic on the device, and even simple programs won't fit. So if you want to do anything really interesting, you have to worry about how much area and resources you're consuming. And we have a lot of passes in the optimization stage that reduce the amount of area we have. The single most important optimization, I think, to deal with that is branch conversion. So we'll look at branch conversion through an example. It's just this here we have a very, very simple CFG, right? One conditional branch. And the first thing we do is to analyze the control flow to each basic block. And anything that's conditionally executed is important here. We build up BDDs, binary decision diagrams, and any non-constant BDD represents a conditionally executed block. Once we've constructed our BDDs, we can predicate all the instructions in A and B in this case. If the branch was false, then we're going to predicate the instructions in A. And if the branch was true, we're going to predicate all the instructions in B. We have specialized hardware to handle predication, or for load stores, or anything with a side effect. Anything that can touch memory, we can predicate all of those. And we can also use select instructions to choose between instruction streams. So after this, we can now combine A and B together, and that branch becomes unconditional. We have a single predecessor to C now, so we're just going to convert those phi nodes into select instructions. And select instructions are very cheap to implement on an FPGA. Because we've merged A and B, we now have the opportunity to save a lot of area by merging functional units. A and B had exclusive predication by the nature of design. And so any shared functional units between them can be collapsed together, and we can just select between the inputs to them. And we can save quite a bit of resources this way. But as we can see now, this is a really simple CFG, and there's no reason for all these basic blocks. So as a final step, we simplify the CFG again, and we collapse everything together. So branch conversion will squeeze the majority of the CFG for us into a single basic block. The exception tends to be loops, where the innermost body will be a basic block, and you'll have a couple of basic blocks before and after each loop nest. This allows us to save lots and lots of area. With the functional unit merging and the increased instructions count, which provides more opportunity for optimizations in the basic block, you can reduce how many resources you're going to consume. We're also not hurt by having this increased instruction count. Because we have so much parallelism on the device, it's not a problem for us to schedule all of these things in parallel at all. So it's optimizations like these that let us fit things onto the device. How do we worry, since we're making accelerators, how do we get them to go fast? And OpenCL is great for pure parallel, embarrassingly parallel algorithms. But it's not always simple to express your algorithm in an embarrassingly parallel fashion. Some really important algorithms need to carry state. So how do you improve the performance of a single thread? Our answer to that is loop pipelining. So here's a very simple OpenCL task. It's performing sort of a silly accumulation. It operates on a single thread, and the data for each iteration is dependent on the result calculated in a previous iteration. So we have this dependency that's going to bottleneck our performance. So loop carry dependencies. It's just some iteration being dependent on a previous iteration. In this case, we can't proceed until we know what the next state will be. And so iteration 1 is dependent on iteration 0, and iteration 2 depends on iteration 1, and so on. All that really matters here, though, is that we figure out what the next state will be. And after that point, we can parallelize the rest of this loop. Once we know what the next state will be, we're free to launch an iteration because there are no more dependencies that we have to calculate to prevent execution. And so the rest of our loop here can run in a parallel fashion using our pipeline parallelism that I showed you with the vector add example. So what this looks like without loop pipelining is each iteration's executing sequentially, and you don't have any overlap. So the loop's going to take a long time to execute. With loop pipelining, though, as soon as you calculate your dependencies, you can launch a new iteration, and now you can start to overlap the execution. And overall, your loop is finishing much more quickly because you're exposing parallelism. So the real difference between loop parallelism and the ND range is just that you can't always resolve your dependencies in a single cycle. Sometimes they're very complicated. And while you're always trying to minimize the amount of time you can launch an iteration, it's not always possible to have it down to a single cycle. So loop pipelining enables to extract parallelism from a single thread while maintaining the ability to communicate state from iteration to iteration. So if we go back to this accumulator, this is a simplified view of what the data path is going to look like. Now we can launch a new iteration in each cycle, but overall each iteration is still taking multiple cycles to complete. And so we can see that iterations are going to flow through this pipeline, much like threads were flowing through our pipeline for the vector add. So what's going to hurt loop pipelining the most? And the answer is memory dependencies. We've had to spend a lot of effort improving dependence analysis, especially loop carry dependence analysis. I can't overstate how much this affects performance. Like I have it on the slides that this can lead to more than 100x, and that's conservative. Our load stores to external memory take a really long time to execute. Going to DDR is slow. So anytime we can reduce a false dependency on a critical path is extremely important to us in order to increase performance. So we've done things like added a complex range analysis to help dependence analysis and reduce false positives. We also have some specialized knowledge of our hardware and programming model that we can leverage. For example, we are going to separate disparate arrays in your program into separate address spaces so that we don't find aliasing between them. We're going to analyze the pointer ranges for each load store unit that can talk to the same piece of memory, and we're going to bank it so that each load store is only talking to a smaller subset of the actual physical memory addresses. And we can look at what banks all of these load stores are talking to, and if they don't talk to the same banks at all, then obviously there's no dependence there. So that being said, what we have right now isn't good enough. Probably it will never be good enough as long as we have a false positive. We're always looking for ways to improve dependence analysis. Any little tricks we find, we try and implement because it has such a large impact on our performance. So I want to round out the talk by discussing some of the issues we've had with LLVM and maybe some of the features we'd like to see implemented. It was really useful to me to attend this developers meeting because lo and behold, there are actually a lot of things coming down the pipe that we can make some really good use out of. So the intrinsic system doesn't support structs as a type. I should take a caveat, sorry, for a second. We're not on top of trunk. We've sort of diverged from the trunk. But I've tried to keep up with what's going on, and I apologize if some of this information is sort of out of date. To implement our predicated intrinsics, we've actually just extended call instruction. And we've modified the class identification system so that regular load stores and predicated load stores both appear as load stores through the ISA and the CAS systems. The pass managers, in terms of runtime, can be really problematic. As I keep mentioning, dependence analysis is very important to us. It's also very slow as an n-squared algorithm. And sometimes we can't avoid running module passes. And having to rerun a function pass, when you only need a single function analysis within that whole module analysis, is not efficient. And so we've implemented a workaround internally to be much more selective in terms of what analyses you're going to run. The on-the-fly pass manager non-inheriting analyses is another case where runtime can be really adversely affected. And we have to be very careful when we're structuring our pass ordering to put everything together so that we reduce the number of times we're rerunning everything. We've run into a lot of, well, maybe not a lot, we've run into several scaling issues with LLVM passes that I doubt probably any of you have seen. We do a lot of unrolling. We'll happily unroll a loop with hundreds of thousands of iterations because we have such large amounts of internal bandwidth. It's not problematic for us to have that much data going around the chip, and unrolling it actually increases our performance significantly. We also inline every function. And after things like branch conversion, we end up with basic blocks that are well over 100,000 lines of code. Lines of code is a bad indicator for us in terms of how many resources we're going to use, but it has a lot of effects on standard passes, runtime. And we've had to make quite a few changes to basic passes like dead store elimination, common subexpression elimination, GVN's one that's problematic quite a bit, and several other passes to keep runtime under control. Loop representation is important to us as well. Well-formed loops are really important to loop pipelining, and we've had to disable quite a few optimizations that will introduce extra loops into a program. Jump threading comes to mind as a particular example. It likes to split back edges, but that for us leads to very poor performance. And so we've had to go through, and if we're running for the FPGA, we disable quite a few things. It's also interesting that a while one loop with no return is actually very useful to us. It's a natural way to describe a piece of hardware that has no end, where you're just going to stream data through your chip. But some of these optimizations like to look at that and be like, well, you must not really need that, and it starts to try and optimize it in funny ways, splitting the loop into multiple loops and doing odd things with the CFG. So it'd be nice if there was some way we could treat loops as more first-class citizens, I guess, and have some way to at least say, I want to preserve loop structure over doing some other optimization. That's really important to us. Some of the features we would like to see added perhaps would be conditional preservation of analyses. I really enjoyed Chandler's talk, and it looks like his new pass manager system will actually allow us to accomplish a lot of what we'd like to do. So I'm really pleased to see that and to see how that works out. We have to support Windows, and we can't force our customers to use a particular compiler. So Windows debug support from Microsoft Visual Studio would be a big plus for us. Dwarf support in Linux for LLVM is quite good, and we've built it into some other tools we have to emulate and debug our kernels so that you can execute your host program and break into your kernel. Not running on the FPGA, but running an emulated version of your kernel, and you can get live state. And that's quite useful to coding up your algorithm, and we just don't have the same support for Windows that we do for Linux. And anything you guys can do to help with dependence analysis as well, since it's so important, would be very beneficial to us. Hal's talk was very good about that, and I'm looking forward to going back and trying to pull in some of his alias scoping and finer-grained alias analyses. But any little tricks you guys have to reduce the false positives in dependence analysis would be very, very useful. So thank you for taking the time to listen. Hopefully you guys have an idea now of that you can at least use LLVM to target things that are vastly different from what you might be used to targeting. Things with no architecture at all. If you're at all interested, I've attached some references to the slide deck. You can take a look at some of the things we've been able to achieve with our compiler. And some of them are really impressive. Not to just be a sort of marketing guy, but some of them really are impressive. And I've also attached some links about our hardware itself if you're interested in learning about FPGAs. Thank you. If there's any questions, I'm happy to answer.
You described elastic pipelining, or you mentioned it. What is that?
Right, so if I go back very early, maybe it's easier just to jump back. When I showed you that pipeline of that simple program, it assumes that every instruction is going to be able to execute in every cycle. So this is assuming that you're never going to have a stall. Like memory's not going to stall. And what the elastic pipeline provides is the ability to handle stalls and bubbles in your pipeline. You're carrying a valid bit and a stall bits going backwards through your pipeline. And it allows you to provide back pressure onto your inputs so that you can not just lose data.
So you've got impressive processing power, and you mentioned the memory was slow. So I guess on-chip memory must be pretty fast, like in the cycle. But then have you implemented something like automatic double buffering or something like that to get data from the DDR so that it doesn't break the performance of the global system?
I mean, so in the end, when you're accessing memory, from the point you want to issue your request to the point it's coming back to your chip is going to be a long time no matter what. And at some point, you're going to be waiting for that memory. Because we have an elastic pipeline, we can fill in all the side paths and continue pooling up data. We do things like dynamic memory coalescing so that we'll reorder addresses on the fly to create nice DDR bursts. And we can do coalescing in the IR itself to collapse load store units together that are going to be sequential access. So we access overall less external memory. And we have several things like that we can do to try and make your memory access more efficiently. But in the end, load store units tend to be slow when you have to wait for external DDR.
So I have a question. So earlier you said you're going to map your hardware on your program description maps basically to its own architecture, but in the end there's going to be some underlying fabric that you're running your FPGA on. It's going to have, it's inherently two-dimensional interconnect. Where is that architecture information feed into your compile flow?
So we try and abstract as much as possible from the user so that they don't have to know all the specifics. The idea is that our backend could map to an ideal sort of configuration. The FPGA, for those who don't know, is made up of a bunch of mostly combinational blocks of lookup tables and registers. It also has a bunch of random access memory and some DSP cores. And you can configure them in various ways. So the idea is that we're going to create just any kind of hardware design that's well pipelined so that you can afford jumps from logical unit to logical unit. And these individual logical units could be stitched up together to perform much larger functions, but they can implement any function. And so that part of it, like the actual underlying FPGA architecture, can be abstracted from the user. What can't be abstracted from the user is the fact that we're creating a pipeline data path. And that's what users have to know about to get really good code for the FPGA. But if you want high performance code on any architecture, you need to know about your architecture.
What kind of loop analysis or optimization you guys are doing in LVM or you want to do?
Well, obviously we use loop info heavily. We have loop-based dependence analysis that goes beyond what's implemented in LLVM. We have transformations that are looking specifically at loops like loop pipelining. We have a lot of stuff that will consider it, that tries to take into account what our pipeline looks like. So as a sort of an aside, it's not always beneficial to perform things like loop invariant code motion because now you're losing locality and you don't want to carry things through the pipeline. So we have things that almost look at it from reverse direction and keep things in the loop. We have a few passes that will sync things back into a loop, which sounds counterintuitive, I'm sure, to a lot of you.
Any data on performance comparison like between the code generated by your compiler and hand-coded Verilog?
We've done some comparisons, yep, and we're always looking to improve there. In general, we tend to use a few more resources than hand-coded RTL. but we can achieve very similar levels of performance, like throughput. I don't have on my slides a particular example, but we are currently actively working on benchmarking and improving against hand-coded RTL all the time.
What about comparing to CPUs? Like, okay, so why would I do that on an FPGA? Obviously, I want some crazy performance boost, right?
Right.
FPGAs are expensive.
They are. It's true. We tend to more compare ourselves to GPUs and other sort of heterogeneous acceleration. So we have an example on that examples design page of an Asian options Monte Carlo stock simulation. And from the literature we found for the GPU, they were able to do about 10 billion simulations a second. And with our pipeline data path, we were able to do 12 billion simulations a second. And we were able to do it at 40 watts of power compared to over 200 for the GPU. And when you're considering putting these things in a large server cluster, power is really going to become much more important. And the FPGA being a much lower power chip than a GPU, for example, you have a much larger gain there. And in some places, that's much more important than even just raw performance. You can also leverage the FPGA's very specific IOs. We have a lot of high-speed IO. It's very easy to connect like a 10G Ethernet input or even higher if you wanted to write a little bit of interfacing code to that IO. And you can code with it in C in a very natural manner. We have, if you look through our examples, look for some examples with, we call them channels, but they provide streaming input and output.
What does your compile time look like?
It ranges. The majority of our compiles are seconds, easily under a minute, order of seconds. Some compiles blow up because we still have some scaling issues. We try and get those under control, and overall our goal is to keep it under a minute. And most of them are there. Some of them, obviously, we have some significant outliers, but we're always working on that.
Well, and you have Quartus spending an hour
right.
doing that afterwards.
So when I say our compile times, I only think of up to producing the Verilog file. After that and feeding it to Quartus is ranging anywhere. If you have a very small design, it's a few hours. And if you have a very large design, you could be looking upwards of a day for a very complex design. That's very close to being full on a large device.
How do you deal with open-ended loops? While some condition, keep going.
Those actually work extremely well on the FPGA. As long as your exit condition could be calculated within a cycle, you can just pipeline that loop very effectively and just keep launching iterations into it. And so you can really leverage the pipeline parallelism. And it's actually a really natural way to express a streaming algorithm. Something like you have Ethernet packets coming in and going out, that you generally don't want to end. Right. Well, in that sense, the loop body is now a pipeline data path. So multiple iterations are reusing it, yes, but it's in a sort of temporal manner.
Just how human readable is the Verilog output?
Yeah, it's tricky and it's large. It's not unusual for it to be over 250,000 lines. I won't joke. So it's very large, and we have a lot of IPs we instantiate which link into other files. But this is for really complicated high-performance algorithms that are using almost the whole chip. For something very, very small, it's actually quite readable. And if you're making something with a streaming in and a streaming out, the actual interface to the module is actually very, very easy to understand.
So do you have to extend the standard LLVM IR one way or another in order to accommodate your backend?
So we added a whole bunch of intrinsics that represent specialized pieces of hardware. Like we replace all load stores with our intrinsics, and we annotate a lot of metadata onto the IR. Metadata for us is in no way optional, at least most of the metadata we use. We use it to determine specific styles of load store units, because we look at access patterns, and a sequential access pattern is going to get a different piece of hardware than something that's totally random. It can be much cheaper.
One more question. So normally for a backend, they see like a standard flow of a selection DAG, machine inster, MC inst, blah, blah, blah. So like the instruction scheduling. So I didn't see any of those in your backend. So still, I imagine it's going to be vastly different from the traditional backends.
We're generating Verilog directly from the IR. I mean, we have an intermediate step of generating a control flow graph, but it's really just built on top of the IR. And we perform we solve a scheduling problem to minimize the amount of logic in the overall design, which would be represented by registers you need that take place between cycles from instruction to instruction.
Do you support only OpenCL 1.x features, or do you consider any 2.0 features for support? And another short question, like related to previous one, like how debugging happens. So like waveform debugging might be a bit tricky if your design is really complicated. You provide alternative ways to do that?
Standard-wise first, we've implemented some 1.2 features, and we're working towards full 1.2 compliance. And after that, we'll be working towards full 2.0 compliance. So it is on our roadmap, and we are moving towards it. It's going to take us time to get there, because it's quite a bit different than other architectures. As for the back end, I'm sorry, could you repeat the question, Ida? Okay, so we provide an emulator tool, and that allows you to functionally verify your algorithm. It runs along with it. OpenCL is the host and accelerator. So you have some host code and you have some accelerator code. And we put the two together in an emulator and we run it, and you can guarantee your functional correctness. And then we go through and generate it, and you can run it in hardware. We have other flows we're developing that I don't think most users would ever need that can do simulation, but you don't want to have to get there. You shouldn't, and you shouldn't have to. Our goal is you never have to. Emulate, generate hardware, see it run. Profile it. We have a profiler that will describe all of your stall natures and show you where you're losing performance.
One more question, I think.
In your example where you had an if-then-else and followed by a merge, are you always executing both clauses of that is in hardware?
Sort of. We're going to do functional unit merging, right? So if there's shared hardware between them, really there's only going to be one copy of it.
Okay, but if it's...
But otherwise, yes. Right. And we'll just predicate it. The important thing to remember, and I'm sorry I forgot to mention it earlier, is that even if an instruction in your program is executed 1 in a million times, you have to have hardware for it. So you might as well just run it and predicate it. It's not costing you a lot of power. Like overall, the FPGA is still very low power. So just run everything and choose the result you need.
So even if you have a multi-way branch, like an n-way branch, you're still going to, of course you need the hardware for it, but you're still feeding the data through all the paths.
And remember, we're collapsing as much as possible into one single large basic block. And our scheduling can figure out everything that can run in parallel. We can do more parallelism than anything else you've seen.
Okay, that's it. Let's thank the speaker.